Okay, the topic today is writing formulas. Ionic compounds with transition metals is what we focus on. Ionic compounds with transition metals. Let's look at periodic table. Remember, periodic table, this section is transition metal. This section in the periodic table is transition metal. And groups 1A through 8A, excluding this section, are called main group elements. Okay? Again, this is transition. All of these are transition metals. Then these are the main group elements. Okay? So when we did the ionic compounds, the binary ionic compounds, we were able to look up the charges. Okay, for every main group element, you want to know the charge. You can easily look it up. For every element in group 1A, it has +1 charge. So you can write the cation and the anion easily by just looking it up. But with transition metals, you cannot get it from the main group elements. Why? Because you cannot predict their charges. Transition metals each element can form more than one type of cation. Okay, so let's look at Roman numerals. So when we do the we want to know the cation. We can look it up in the main group. Only the main group elements we can predict the cations or anions. But with transition metal, we write it this way. Okay, it says ion 2 to remind you about Roman numerals. You see, in case you don't know Roman numerals, here it is. Okay, now ion is a transition metal. So ion 2, this 2 is telling us that it's 2 plus charges, telling us the number of charges, but it must be cation. Ion 3, you see, ion 3 is 3 plus. So this is telling us the number of charges, which I think this is easier. Okay, you don't even have to refer to any main group elements with charges. Then copper is transition metal. Copper 1, okay? Copper 1, Cu1 plus. Copper 2, you said this Roman numeral, this number in Roman numeral is telling you the number of charges, which we show here. The manganese, you see, manganese 2 plus, manganese 4 plus, okay? But there are exceptions. There are some transition metals that behave like elements in the representative elements. Okay, that's the main group elements. So they have only one type of cation. Like silver is always 1 plus. Zinc is always 2 plus. Cadmium is always 2 plus. So if you put the Roman numeral, that's wrong. You can't do that because these are exceptions. They can only form one type of cation. So they behave like representative elements. Now, for lead and tin are also exceptions. They are representative elements, but they behave like transition metals. Lead 2, there can be lead 2, you see 2 plus, or lead 4 plus. Tin 2 plus, or tin 4. So these are exceptions that do not follow the rules. Okay? So I want you to write a symbol for the following. Pause the video and write a symbol for the following. Hopefully, you got this. You see 2 plus, 3 plus, 4 plus. Okay? Barium, that's a tricky one. Barium is a representative element and it's not one of the exceptions. So it's not a transition. You can put 2 here. Okay? So the symbol is barium, just barium, then you look up the ion. It's supposed to be barium 2 plus. So that was tricky. Let's do an example of writing like we want to write a formula for these ionic compounds with transition metals. but before we do that, I want you to, you said copper 2 chloride. How do you get this? Iron 3 sulfide. I will refer you to take a picture of this. Take a picture of that. Because when you have a compound, the compound is made up of cation and anion. Okay? Cation and anion. Chloride is an anion because it's, look at it, chloride. You look it up here, the symbol for chloride. You see chloride? This is the symbol for chloride. Okay? Oxide. This is the symbol for oxide. So you can come here to look up the anion. Okay? The cation is exactly the way it is in the periodic table. And remember, because this is not transition metal, we are not getting the charges from here. Okay, the charges is given to you in parentheses here. So let me do these examples. Let's do these 2 examples. In writing the formula, copper 2 chloride, this Roman numeral gives you the number of charges. So you write the symbol you get from periodic table, 2 plus, then chloride. You see, you look up in the chart, chloride is this. So you get, that's chloride. These 2 charges are not equal. The charges must be equal. We do the crisscross, which we've done before. You have, I'm sorry. Okay, copper 2 chloride. Then we are done. What does this mean? It means there are this, and then you have 2 of this. If you check, you see the charges are equal. You add these 2, you add this, they're equal. Then this is a neutral compound, neutral ionic compound. Okay, now for this one, the symbol for ion is that it has, this is the charge, then sulfide, that's the anion. You have a charge. Okay, so we got this. So you have Fe2. These 2 become the subscript. These 3 become the subscript. Okay, and this means there are 2 of this, 3 plus, and there are 3 of this S, 2 negative or 2 minus. You see that? You add this up, is 6 negative, you have 6 positive. They're equal. So you have a neutral atom. The charge must be equal. Okay? So that's an example. So I'll give you a practice question to do later. But let's do this first. I want you to watch this video.
Let's talk about transition metals in ionic formulas. So the transition metals are the elements in this part of the periodic table here. And when we write formulas for ionic compounds that contain transition metals, the formulas look like this, with these Roman numerals here in the middle. So this might be a little bit different from other types of chemical formulas you've seen. So in this video, we'll talk about what's going on here. Okay, so transition metals. As I said before, the transition metals are the elements in this area here of the periodic table. I've written some of the most common ones in. Now, I'm also going to be talking about some of the metals over here. Okay, these guys here aren't technically transition metals, but they act a lot like the transition metals in certain ways. So I'm going to be including them in the discussion as well. Now, for ionic bonding and ionic formulas, transition metals are a little bit different from the elements here and here on the periodic table. This is the reason why. Transition metal elements, or at least I should say many of the transition metal elements, are able to make more than one type of ion. And each one of these types of ions has a different charge. Let me show you what I mean by this. Let's start by taking an example that's not a transition metal. We'll take lithium in this column here. Okay, so lithium. When lithium forms an ion, we know that that ion is going to have a +1 charge. And that's because lithium is in this column. every single ion that lithium makes is always going to be +1. We know that based on its location. Now, the same is true for calcium. Okay, calcium is in this column here. So when calcium makes an ion, that ion will be Ca2+, and it will always, calcium will always make ions that are 2+. Every single calcium ion, for the most part, will be Ca2+. Now, on the other hand, transition metals are a little bit more loosey-goosey about things, okay? Iron, Fe for example. Iron can make an ion that's 2+, but it can also make an ion that has a 3+ charge. So it's able to make both these types of ions. Gold, which is another transition metal right here, can make Au1+ with a 1+ charge, or it can make a type of ion that's Au3+. Manganese, which is right here, is one of the craziest of the transition metals because of the huge variety of ions that it can make, okay? A manganese element can turn into Mn2+, or Mn3+, or Mn4+, or Mn6+, or Mn7+. So the point is, the transition metals can make multiple types of ions, and these ions all have different charges. This is different from the metals over here and from other types of elements on the periodic table, which tend to always make the same type of element based on what column they're in. Now, sometimes people ask, why is it that the transition metals are able to make this wide variety of ions? And the answer is kind of complicated, but basically it has to do with the way electrons are arranged in the orbitals of the transition metals. Essentially, the transition metals are more loosey-goosey with the electrons that they give away. They're not set on giving just one away or two away. They can give a couple away, they can give a couple more away, and so that's how you end up with these ions that have varying numbers, varying amounts of positive charge. So, when we have these elements that can make different types of ions, how do we tell them apart? Well, we have to use a naming system that uses Roman numerals. I'll show you what I mean. So using this Roman numeral notation, we call the Fe2+ ion, we call that iron 2, with a 2 in Roman numerals in parentheses. Iron 3+ is iron 3. Gold 1+ is gold 1. And manganese, for example, 4+, 6+, 7+, are written as manganese 4, manganese 6, and manganese 7. Now, you might be a little bit unfamiliar with how to write numbers in Roman numerals, so it probably wouldn't hurt to do a real quick review of Roman numerals before we move on. So here's how to write the numbers 1 through 10 in Roman numerals, okay? 1, 2, 3 are pretty straightforward. Then 5 is a V, and 4 is an IV because it's 5 minus 1. If a number is to the left, it's subtracted. So 1, 2, 3, 5 minus 1 is 4, and 5. Then we have 6 VI, 7 VII, 8 V with 3 I's, and then we have the same thing with 9. 10 is an X, and 9 is an X minus 1. Now, it's very unlikely that you would run into an ion that had a charge of 8, 9, or 10, but hey, this might just be useful to keep in mind anyway. Nonetheless, 4, 5, and 6 tend to be quite common ionic charges, so you want to be sure to know how to write these numbers in Roman numerals. So we're going to use this Roman numeral notation whenever we write formulas with transition metals, because we have to explicitly say what charge the metal has, because we can't just figure it out based on where it is on the periodic table. So we have to say manganese 2 chloride for a compound that contains Mn2+. For iron 3 oxide, we write that so that whoever's reading it knows that we're talking about a compound that contains iron with a 3+ charge. Okay? This Roman numeral notation is different from formulas without transition metals, where we just write calcium fluoride, or we'd write sodium sulfide. We don't have to use Roman numerals when we write formulas without transition metals because it's totally clear what these charges are, right? Calcium is in this column here, so we know for sure that it's 2 plus, and it's always going to be 2 plus. Sodium is in this column here, so that we know that it's 1 plus, and it's always going to be 1 plus. So we don't have to use Roman numerals when we write formulas without transition metals, and in fact, it would be wrong to use Roman numerals when you're doing this. So don't put Roman numerals into the formulas unless they have transition metals. So that's an introduction to transition metals in ionic compounds. We saw how one transition metal element can make multiple ions with different charges. In the next 2 videos, we're going to learn how to take the name of a transition metal compound and write a formula for it.
So with what you've listened to and with the examples I've given, you should be able to write a formula for the following. And show your work as I showed in the example I did earlier. Show the example, pause the video and write the formula for the following. Hopefully you got this right. Hopefully you'll be able to recognize that silver bromide is an exception. Silver is a transition metal, but there's no one here. Why? It forms only one kind of cation. And another exception here is lead-4. Lead is in a representative element, but it forms 2 types of cations. It behaves like transition metal. Then I hope you take note of that. We just have to simplify it like in your math class. Okay, 2,4 we simplify it and it become, this is supposed to be small subscript, okay, not big 2. Okay, that's my mistake there. Hopefully this makes sense. Thank you.